Welcome to this session. We will continue whatever we left in the last class. In the last class, we are looking into the a two-dimensional transient heat conduction problem in a cylindrical polar coordinate system, and we used a separation of variable type of solution, and we have found out that the theta varying part constitutes a standard and independent eigenvalue problem, and then we have formulated the radial varying part, and we will be looking into the rest of the solution. So, if you look into the radial varying part, this is the governing equation along with these two boundary condition, and if you now remember that these are nothing, this is nothing but a Bessel equation of nth order, and the solution is composed of Jn and Yn. So, C1 Jn lambda n lambda r plus C2 Yn lambda r. So, these are this is the solution, and now if we look into the, if we put in the boundary condition, if we know the definition of Yn, if you Yn is infinite at r is equal to 0. So, therefore, in order to have this boundary condition that at r is equal to 0, capital R is finite. So, this is in opposite to the definition of Yn. So, in order to do that, so in order to comply that one, the associated constant has to be equal to 0. So, that I will be getting a bounded solution of R. So, C1 RR is nothing but C1 Jn lambda r. Now we put the other boundary condition at r is equal to 1, capital R is equal to 0. So, therefore, C1 Jn lambda is equal to 0. For a non-trivial solution, C1 is not equal to 0, therefore, Jn lambda is equal to 0. And if you look into the variation of Bessel function as a in terms of lambda, so they will be assuming a finite value, and then they will be oscillating along the x axis or lambda axis at infinite and cutting the they are oscillating about the lambda axis with a diminishing magnitude, and they will be cutting the lambda axis at infinite number of times, and each of these intersection point is the eigenvalue to the system, and the eigenfunctions are the nth order Bessel function. So, therefore, we will be having the we will be writing J1 lambda m n is equal to 0. So, there will be infinite number loop for every n varying from from 1 to infinity. We will be having m roots of Jn. So, therefore, the eigenfunctions are written as R m n as C1 Jn lambda m n r. So, these are the eigenfunctions. Roots of these equations are the eigenvalues, and lambda m n is nothing but mth root of Bessel function of first kind of order n. So, now we have seen that both theta varying part and r varying part, they constitute an independent eigenvalue problem. So, therefore, we can constitute the complete solution by doing a double summation of individual part of the eigenvalue problem. And if you look into the time varying part, the time varying part will be nothing but T m n dt m n dt will be nothing but minus lambda m n square times t lambda m n square. So, T m n will be nothing but another constant, let us say C3 exponential minus lambda mn square times t. Now, we can superpose all the three solution and construct the complete solution. So, the complete solution will be a double summation. Okay. So, u r theta t will be nothing but summation n is equal to 0 to infinity, m is equal to 1 to infinity, exponential minus lambda m n square times t, j n lambda m n r multiplied by d m n sin n theta plus e m n cosine n theta. So, at t is equal to 0. Now, these two constants d m n and c e m n will be evaluated from the initial condition at t is equal to 0, u is equal to u 0 r theta. So, therefore, u 0 r theta will be nothing but double summation 1 over m another over n j n lambda m n r d m n sin n theta plus e m n cosine n theta, and by using the orthogonal property of the sine functions, one can evaluate the d m n and e m n. So, therefore, d m n will be nothing but we have done it several times, r equal to 0 to 1, theta is equal to minus pi to plus pi, u 0 r theta r j n lambda m n r sin n theta dr d theta, and r is equal to 0 to 1, theta is equal to pi to minus pi to plus pi, r j n square lambda m n r sin square n theta dr d theta, and similarly we can get an expression of E m n as r equal to 0 to 1, theta is equal to minus pi to plus pi, r j n square lambda m n r cos square n theta dr d theta, and 0 to 1 minus pi to plus pi, u 0 r theta r j n lambda m n r cosine n theta dr theta. So, that gives the complete solution of the cylindrical coordinate system, the partial differential equation for the cylindrical coordinate system, and we can have seen that how the eigenvalue problem can be formulated in the theta direction, and in the r direction they will be constituting the independent eigenvalue problem, and the overall solution can be obtained by using a Lie principle of linear superposition by doing a double summation. Since there are two independent eigenvalue problem, we are having a double summation in the solution, and the associated constants will be evaluated from the orthogonal property of the eigenfunctions. Next, we will be moving over to the spherical polar coordinate system, which will be quite popular whenever we will be looking into the transport properties occurring across the spherical system, spherical coordinate system, and spherical vessels or things like that. Then let us look into the Laplacian in spherical coordinate. Okay. what is Laplacian in the spherical coordinate? It is del square u is equal to 1 over r square del r square del u del r plus 1 over r square sin theta del theta sin theta del u del theta, okay, plus 1 over r square sin square theta del square u del phi square. So, that is the Laplacian in a spherical coordinate system, and the domain of r is varying from 0 to capital R or 0 to 1, theta is equal to from 0 to pi, and phi is varying from minus pi to plus pi. Now, we will be looking into the first example. Example 1 is Laplacian of u is equal to 0, and where the domain is r is basically varying from 0 to 1. At r is equal to 1, we have u is equal to f of theta, or it may be a constant as well, and there is a phi symmetry. So, any derivative del phi del square del phi square all are becoming 0. So, since there is a phi symmetry, so this term will be off. So, it becomes a two-dimensional problem. So, let us look into the two-dimensional problem. One over r square del r square del u del r plus 1 over r square sin theta del theta sin theta del u del theta will be equal to 0. Now, we assume that u is we go ahead with a separation of variable type of solution, r of r multiplied by t of theta. Okay. So, if you put these in the governing equation and then divide by r and t, separating the variables, we will be getting 1 over r d dr r square dr is equal to minus 1 over t sin theta d theta sin theta dt d theta, and again this will be equal to some constant, that constant is equal to lambda, and conditions on theta are coming from the boundary physical boundary condition. Condition on theta will be coming from the physical boundary conditions. Theta is equal to 0, t is bounded, theta is equal to pi, t is bounded, theta is equal to 0, t prime is bounded, and theta is equal to pi, t prime is bounded. So, these boundary conditions have to be satisfied, and theta is basically varying from 0 to pi. Okay. So, next what we will do, we will be substituting small t is equal to cosine theta and see what we get. If we substitute small t is equal to cosine theta, let us see what we get. 1 over sin theta d theta sin theta dt d theta plus lambda t will be equal to 0. So, dt d theta will be nothing but dt dt times dt d theta. So, this becomes minus sin theta dt dt, and sin theta dt d theta will be nothing but minus sin square theta dt dt, and this will be nothing but minus 1 minus cos square theta dt dt is equal to minus 1 minus t square. So, I express sin theta dt dt in terms of t and capital T. Okay. Similarly, we do for the other variable d d theta sin theta dt d theta is nothing but d d theta of minus 1 minus t square dt dt, and this will become dt d dt of minus 1 minus t square dt dt is nothing but dt d theta, and dt d theta is nothing but minus sin theta. So, it becomes minus minus plus. So, it becomes sin theta d dt of 1 minus t square dt dt. So, 1 by sin theta d d theta of sin theta dt d theta is equal to 1 over sin theta d d theta sin theta dt d theta is nothing but d dt of 1 minus t square dt dt. So, I can put in a neat form as d dt t of 1 minus t square dt dt plus lambda t is equal to 0, where the dummy variable t is nothing but it varies from minus 1 to plus 1. Now, what is this? This equation is nothing but a Legendre equation if lambda is represented as n into n plus 1. So, solution of this equation will be constituted of Legendre polynomial and Legendre function. So, t of t will be nothing but C1 Pnt plus C2 Qnt. So, Pn is nothing but Legendre polynomial of degree n, and Qn is nothing but the Legendre function of degree n. Now, eigenvalues are lambda n is equal to n into n plus 1, where n runs from 0, 1, 2 up to infinity, and we know the property of Qn, that Qn is not bounded, it is unbounded at plus 1 and at t is equal to plus 1 and t is equal to minus 1, but we have a finite value of the solution. So, therefore, the associated constant is equal to 0. So, the Qn is unbounded at t is equal to plus minus 1. So, therefore, the associated constant C2 is equal to 0. So, the solution of theta varying part will be nothing but C1 Pn t. So, therefore, Tn of theta will be C1 Pn cosine theta. So, these are the eigenfunctions. Now, let us look into the radial direction. In r direction, we have 1 over Rn d dr r square drn dr minus lambda n is equal to 0. So, therefore, we have d dr of r square drn dr minus lambda n rn is equal to 0, and lambda n will be basically n into n plus 1. So, just open this up, open up this differential r square d square rn dr square plus 2r drn dr minus n into n plus 1 rn is equal to 0. Now, if we remember the special ODEs that we have already discussed earlier, this particular equation falls under the category of Euler's equation. So, this is nothing but the Euler's equation, and we have already discussed that the solution will be in the form of r to the power alpha. The Rn will be in the form of r to the power alpha. So, if we put r to the power alpha there, then what we will be getting is that we will be getting a characteristic equation in alpha. Characteristic equation in alpha, and that becomes alpha into alpha minus 1 plus 2 alpha minus n into n plus 1 will be equal to 0. So, it becomes alpha square minus alpha plus 2 alpha, so it will be plus alpha minus n square minus n is equal to 0. This can be factorized, alpha minus n into alpha plus n plus 1 is equal to 0. Therefore, it will be having two roots, alpha will be n and minus n plus 1. Okay. So, once we get the get this, then we will be getting the solution of R n as R n, which will be function of R is C 2 r C 2 n r to the power n plus C 3 n r to the power minus n plus 1. Now, we put the boundary condition at r is equal to 0, R n is finite. So, if R n is finite, then this term will blow off and it becomes infinite. So, therefore, the associated constant must be equal to 0. So, C 3 n must be equal to 0 and R n r is equal to C 2 n r to the power n. So, u r theta is nothing but summation of n is equal to 0 to infinity C n r to the power n p n cos theta. So, this becomes the solution of u varying part of the problem, the in two dimensional problem. Now, only one constant now needs to be determined, that will be the constant C n, and that constant will be determined from the boundary condition located at r is equal to 1. So, we have the unutilized boundary condition at r is equal to 1, u r theta is given as f of theta. So, from this boundary condition we will be evaluating r is equal to 1, u of r theta is nothing but f of theta, and f of theta will be therefore summation of n is equal to 0 to infinity C n p n cos theta. Now, we will be the Legendre polynomial, like the Bessel functions, the Legendre polynomials are orthogonal. If you remember, we have iterated this in the while we discussed the properties of the Legendre polynomials. They are orthogonal functions, but with respect to weight function sin theta. So, we utilize the orthogonal property of the Legendre polynomial, and we can evaluate Cn as integral 0 to pi f of theta Pn cosine theta sin theta d theta and 0 to pi Pn square cosine theta sin theta d theta. And it can be shown that denominator is nothing but -1 to +1 Pn square t dt, and this will be 2 divided by 2n plus 1. So, Cn is nothing but 2n plus 1 divided by 2, 0 to pi f of theta Pn cosine theta sin theta d theta. In fact, the numerator can also be simplified in terms of there are recursive formula of the Legendre polynomial. So, that completes this problem in the spherical polar coordinate system. Now, in the next class, what we will be doing? What will be taking up one more problem on spherical coordinate system, which will be a higher dimensional 3-dimensional problem, and we will be solving that equation, and then that will be completing the problems, the partial differential equations in rectangular coordinate system, in cylindrical coordinate system, and spherical polar coordinate system. After that, what we will be doing? We will be looking into 2 more realistic problems, which will be quite actually occurring in a heat conduction problem, and which will be giving rise to a general formulation of an actual problem that will be having the various types of non-homogeneous boundary conditions in different boundaries. Then we will be at the higher dimensional problem, how to tackle the various types of non-homogeneities in the boundary conditions, and we will be breaking down the problem into sub problem and converting them into the whole post problem, and will be going ahead with the complete solution. So, I stop here in this class. We will be taking up this one more problem in the spherical polar coordinate system in the next class. Thank you very much.